Alright guys, the goal of this video is to go over linear regression. This video is going to be split into three parts. The first part is just going to go over kind of a list of steps, that kind of what your homework needs to look like. Step number two, or second part, is going to be going over why it works. And the third one is, since this graph right here is going to be parabolic, and we usually focus on parabolic early, I'm going to show a non-parabolic shape just as an example at the very end. So what is the purpose of linear regression? Essentially what we have right now is the ability to find the equation of a general line, y, x. And this first question says, what is the difference between a specific and a general equation? Well, the general equation is that y equals mx plus b, or we use kx plus b in class. Simply put, the answer to this question is right here, these constants. You currently have the ability to find this one because on a line it's the slope, and this one because it's y-intercept, which we've talked about how to find those in a separate video as well as in class. What is the specific equation? We want to find k and b. Now, linear regression is meant to find these particular ones for a nonlinear shape. You cannot use slope and y-intercept. You cannot use that old method because that's not a line. So what does it need to look like? Well, as you see the numbers right here, this is the information we used in class. I'll use it as an example going forward, but let's real quick just go to the list. Linear regression, how to find the equation of a nonlinear function, aka, switching that title real quick, how to find the constants, like we talked about on the last slide. The whole goal is to find those constants for an equation that looks maybe like this instead of that one, the nonlinear kind. So what are our steps? The first step is to graph the original data. I'm going to flip through this real fast and come back. Okay, so this is that sample data from the other page, x versus t. You can very clearly see that it makes a nonlinear function. Then identify what that shape is and therefore the equation. So we go back to that thing, we go, all right, that is very obviously a parabola. So this is y equals kx squared plus b. Or if you want to replace the variables, you certainly can. I'll say x, because you can see the position right over there, is equal to k times t squared plus b. T, in that particular case. What's next? Okay, number three, whatever is making it a line should be graphed in order to get it to be a line. AKA, if you look at this equation right here, which you should have available, okay, you can see that if I graph x versus t, it will always, 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 always make a parabola, as well it should. Okay? Or another way to put that is that my x, you can see here, is growing way faster than my t. X has actually had its variables squared already. They're increasing in a squared value, so it should be that. So what should I graph instead? Well, x versus t is squared, so it's going to make that happen. But everything inside t squared is to the first power. So if x is to the first, t squared is to the first, and if we look on our next page here, it should make a straight line. Notice what changes is t squared. If you go back to our original set of data, all the way over here, you might say, where the heck is t squared? Well, obviously it's not here. You would make another column of data called t squared, which would have different units like s squared, and then you literally do what it says. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. This is graphed now compared to this in order to get this guy right here. Pay no attention, by the way, to these. These were some, this is the back side of the page, and so it's messing up. But yeah, straight line. You'll notice now the scale is different. On the last page, the scale was, wrong one. The scale was 1 to 5 because I had 1, 2, 3, 4, and 5. And now, because of the squaring of that, my scale is now, here's my 1 right here. That's 1 squared. Here now, right here is my 4 because that's 2 squared. Here's 9, 3 squared, 16 for 4 squared, and 25 right over there. So you'll notice it's not the same thing being graphed anymore. Okay. Once you've done that, you'll notice our new step of graph the new data. That's what we just got done showing. You would make a new graph. Step 5, now literally everything is a remix of what you've already done. Go find the slope and the y-intercept the same way as you always have. So I would grab, oops, sorry, not this one. I would grab points off. I talked about this in class. This actually is perfect data. So if I grab this guy right here, that is 25 seconds squared, comma, 75 meters. And this guy, let's grab this guy right here. This is 4 seconds squared, comma, 12 meters. And so I find the slope. What's the slope? Well, I would take my y2 minus y1, do it in whatever order you want, 75 meters minus 12 meters over x2, notice those units are sticking around, minus 4 seconds squared, and I would get 63 meters over 21 seconds squared, or 3 meters per second squared. This is my k. This is the k that goes right here. Okay, so now I need to calculate my y-intercept, same way as I have done before. I'm just going to plug into this equation. You, by the way, don't have to write this out, but I'm just doing it as a reference. What's my y? Well, I'm going to use this point again. So I'm going to use 75 meters for my y. My k, I just found out, was 3 meters per second squared. My x is 25 seconds squared plus b. Notice but my second squared will cancel because that one's on the bottom and this one's on top. This would end up as 75 meters and 75 meters minus 75 meters would give me a b value of 0. So, again, running through that list, we graphed. We found the equation, the generalized equation. You can use either of these if it helps. And this equation is what tells you to graph x versus t squared in this case. So then we make the second graph. Here it is. Then once we have the second graph, because of reasons I'll talk about in just a second, the k value is exactly the same for this graph right here, as it is for this graph right over here. So what's my final result? My final result is an equation for this nonlinear function, because that was the whole goal. X is equal to 3 meters per second squared times t squared, because this is a t squared function, plus 0 meters in this particular case. And there we have the equation of a nonlinear function. So why exactly does this work? Well, this works simply put because if you come back to this data that we have over here, we have this data right here, you ask the question, what is it that makes it this shape? I kind of mentioned a little bit earlier. Y has already been squared, so the y is growing much faster. Now it's weird when you think about it, but if I punch in again the general equation, okay, this guy, actually I already have it over here, this guy right over here, you want to think about it like this. Here, the input is coming in. So I'm putting in 1, and 2, and 3, and 4. And we already know kind of what's going to happen. Let's imagine we put a 1 in here. 1 is squared. 1 times 3, we get a 3. Or we plug the 2 in there. We square it, and we get 4. Okay, and then 4 times 3 is 12. That's where we're getting our 12 from. Remember, this is, of course, perfect data. And, of course, we're adding 0 to that because of the numbers we calculated a second ago. That's what's making this data happen. So what you'll notice is that these numbers are being squared. So this number has already been squared. So what I'm doing is I'm simply squaring these numbers, squaring all of them, so that I have essentially this situation. A versus B will make, oops, I did that poorly. A versus B make a curve, that's right. If the equation is A equals, darn it, messing up here. My apologies, give me 2 seconds here. Erase, erase. A versus B, yes. Going back. Here we are. Okay, so the equation was A equals B squared. Okay, of course you would get A, you would get B, and we get this parabola here. A versus B makes this parabola. But these have all been squared. So I'm going to square this one essentially as well. So now, if I was looking at a set of A squared versus B squared, then you of course know it'll make a straight line in this case. Now, why does this work? Well, because again, what I do here is instead of now plugging in for x squared and having to square them, it's already been squared. So earlier I said, hey, we plug 1 in here, we square it, and we multiply by 3. Now we don't have to square it. It's already squared. It's 1 second squared. So we're just multiplying by 3. Okay, and next we plug in 2. Well, originally we would plug in 2 to get 4. We don't have to square it. It's already 4 second squared. That's what this is. So all you're doing is taking that 4 second squared, multiplying by 3, 9 second squared, multiplying by 3, 16 second squared, multiplying by 3, and 27. So it's going up at a steady rate. In other words, both sets of data are having the same thing happen. But let me reiterate a very important detail about this. Okay, this is the graph we care about. We don't care about this graph except to go get the constants. That's all we're doing. All we do is grab this. Like I talked about in class, using this method, I can literally move any set of data around any particular way I want and make it look like anything. So why the heck are we doing this? Again, it's to go get those constants. What you can think of is we are actually not changing the data at all. This is the original set of data. We are simply looking from a new point of view. From this new point of view, which is a line, we can grab those constants, and those constants will be the same as this one right over here. Why are they the same? Well, you can see it right here. If I graph x, okay, and then I put a t down, right? The original thing says it's squared, so that's what makes it a parabola. Then I multiply by k, then I add b. But if t squared is already here, okay, t squared is already here. Don't think of it as a squared thing. Now it's all one thing. It's all one thing. Let's call it j. Now it's j, okay? And multiply by k and add b. K, add b. X versus j will always make a straight line. X versus t squared will always make a straight line. But these values, to manipulate this, have not changed. So even though x versus t makes a parabola and x versus t squared makes a straight line, they have the exact same constants, and therefore we can use the constants in the line to get the original. All right, let's do one more sample problem. Okay, just using those steps that we talked about right over here. Graph the original data. So here is the new set of data. I've got mass that is increasing in grams. I've got acceleration in centimeters per second squared. You see these numbers right over here. Okay, so I went and I graphed it. Okay, actually don't pay attention to that yet. Okay, I graphed it, and this is the shape I get. So this is step 1, do the graph. What's step 2? Step 2 is, okay, what is making that not a line? So that is a hyperbolic function. So that's y equals k times 1 over x plus b. And I look at what's making that not a line. Y versus x, or in this case, oops, no, I multiply there. Multiplied plus b. Okay. A versus m will always make a hyperbolic shape. So what is to the first power? X is to the negative first, m is to the negative first, but 1 over x is to the first, or 1 over m is to the first. So I'm going to graph, instead of a versus m, I'm going to graph instead a versus 1 over m. Notice how those units entirely changed down there. How did I do that? You can see that's what that other box was up here for. I took all these numbers and took their inverse, and of course I got decimals. One thing you might notice, there's a bunch of extra decimals here. I just used 2 sig figs in this particular case. I might have used 3, but I like to line up these variables nice, because now instead of worrying about all the decimals or whatever, I can kind of think of it like 17, 20, 26, 35, and 53, which is why you can see on my graph that I go up by, I go up by quote unquote 10. It's 0.0010, 0.0020, 0.0030, all the way up past that original point. And then I graphed the data. You can see right here, I'm getting those particular points. Once I have this new graph, okay, I do that age-old thing, right? I try to grab a point, okay? This point is pretty darn close to the line, so we're gonna call, this is, I think, 0.00531 over grams. So notice the units down here change. Okay, comma, I think the acceleration was 104.6 centimeters per second squared. And then I grabbed, I think it was, let's see here, 0.21. I think it was this guy, because that's pretty darn close to the line. That is 0.0021, 1 over grams, comma, 41.8 centimeters per second squared. Now it's just slope time, right? This minus this, as crappy as those units look, centimeters per second squared minus 41.8 centimeters per second squared, and all of that is over these weird units of 0.00531 over grams minus 0.0021 1 over grams. And as I'm taking a decent number divided by a very small number, as you can kind of imagine, I end up with a very big number. I got 19,600. And what would my units be? It would be centimeters per second over 1 over g. Okay, now it's really icky, so I'm just going to go ahead and multiply this up. I think these units are a little bit cleaner as, let's do this, centimeters per second squared times grams. That's just the inverse of this down here, right there. And then, of course, I would punch that into the y-intercept. So I'm going to lay this out for myself real quick. That should be times plus x. This is 104.6 centimeters per second squared is equal to k, which is that 19,600 centimeters per second squared times g times 0.00531 over grams, which you can see is 1 over grams will cancel with those grams, plus b. By the way, as complicated as these units are going to get, what you can look at simply is, of course, what are the units on the y, since it is the y-intercept, and these, this guy and this guy, of course, better match if I've done this correctly. And I think I calculated my b value to be 0.588 centimeters per second squared, which is pretty darn close, as you can kind of see it's heading this way. Pretty darn close to the 0 right there. So what's my final answer? My final answer should be that my final equation is acceleration is equal to my k value, 19,600 centimeters per second squared times g, that's that, times 1 over mass plus 0.588 centimeters per second squared. We have the constants, okay, and we have the original variables in place, so we have the equation of this nonlinear function. The end.